everybody doing?
Good, how are you?
Good, thank you. I'm good. Good break, hopefully. All right, well, hopefully everybody's here for ME 3500 because that's what this is. Good to see many familiar faces from 2500. Welcome back. And I'm happy to see many new faces as well. So I'm Professor Beetham. I am one of the thermal fluid science professors in mechanical engineering. And this is one of the core courses that I teach. And I also do research in this area. So for anybody who's interested in research, I'm always happy to chat about that. I do research that is computational fluid dynamics primarily, a little bit of experimentation as well, mostly in the areas of environmental and sustainability flows. So things like how do particles settle after a volcanic eruption? How can we turn algae into biodiesel? Those sorts of things. Okay, so before we actually just fully dive into content, I wanted to go over kind of the highlights of the syllabus. I did not print it out because I like the trees and it feels like a waste of paper to do that, but you can find it on Moodle unless I haven't posted it yet. Have I posted it?
The
I,
syllabus?
yeah. Oh, I didn't? Okay, I'll post that right after class. There's nothing really shocking or surprising in it, but I will post it after class. Okay, so first of all, what are we going to learn? This is a fluid mechanics and a kind of part two of heat transfer course. So it's going to be divided up like that, just kind of like how 2500 was with thermo and heat transfer. So we're going to learn about fluid mechanics, as well as heat transfer. And the split is pretty much 2/3, 1/3 for this class in terms of the partition between fluid mechanics and heat transfer. In the area of fluid mechanics, we're going to talk about fundamentals to start things off. We're going to talk about two different approaches for analyzing fluid flows. So these are called integral and differential analysis. We're also going to talk about fluid statics. So that's fluids at rest. We're going to talk about the Bernoulli equation, which if you remember from, I think it was lab 1 in 2500, you actually already used the Bernoulli equation, but we're going to talk about it in a whole lot more detail. And then we're also going to talk about incompressible inviscid flows, which for us is going to essentially mean pipe flow. So this unit will be extremely practical. We'll talk about losses in pipes, how to calculate sort of what sort of a pump you might need to push a fluid through a piping system, all that good stuff. And in the heat transfer side of things, in this course, the sort of the elements of heat transfer that we're going to cover is a bit more depth into conduction. So we'll be looking at the heat equation or the diffusion equation. So we'll be taking what we learned in 2500 a step further. And then we're going to talk about convection a whole lot. So if you remember from 2500, convection is heat transfer when we have a fluid that's moving. So that goes hand in hand with what we're going to learn in the first 2/3 of the course. So we'll do that element of heat transfer some justice. And then last, we'll talk about heat exchangers. Any questions so far on content? Yeah.
How many tables are there going to be?
Actually, very few. So there will be some like small tables, nothing like what you saw in thermo in the heat transfer section. So it turns out for convection, a lot of the things that we're going to use are empirically derived. So you need to look up coefficients for equations in like a relatively small table. Did you not like the tables, Mark?
I'm mid-exam. I have to tear apart my exam. Packets over here, look through it.
I know, it's a lot. Less tables. Any other questions? Okay. All right, so let's talk a little bit about how the class is structured. So those of you who had me for 2,500, it's going to be structured pretty much the same way, but those of you who haven't, I'll kind of tell you how I run things. So obviously we have a lecture period. So lectures are of course going to be in person in this room at the scheduled time. I always record my lectures and post them after class, as well as I will post these annotated versions of the notes to Moodle. Um, so in person, but recordings and annotated notes posted after class. That being said, I do not take attendance, as you may have noticed, but I find that the students who come to class tend to do a bit better. I personally have an easier time engaging with things when I'm physically present. So I strongly encourage that, but we're all adults in this room. So if you are sick, if you need to take care of something else and you need to watch a class, asynchronously afterwards, that is available to you. Obviously, not the case for exams. So exams will all be in person, which I will explain next. So there are going to be 2 midterms and a final. And I have a decent idea of when they will be. I've put that on the schedule on Moodle. So I kind of do a week by week or class by class, what topic we'll be covering and then where the exams fall. It's possible that those could move by a day or two, depending on kind of how things go throughout the semester, but they should be pretty reasonable to where they're at right now. So just for reference, those 2 midterms are essentially going to be fully fluid mechanics based. So it'll be kind of fluid mechanics part 1, fluid mechanics part 2, and then the final will be comprehensive, but there will be an emphasis on the heat transfer stuff. So there will probably be like 1 question that is a review of fluid mechanics stuff that you've already been tested on with the other exams, and then the rest would be heat transfer related. Okay. This class has a lab section, which I'm sure you're all aware of. Just like 2,500, our scheduled, like registered lab time is going to be for lab demos, so we won't use all of them, okay? So labs this week, don't show up. You don't need to do that. We're going to introduce lab 1 next week, however, so plan to show up to lab 1 of the demonstration times next week. So scheduled lab time is for demos. And speaking of demos, you can go to any demonstration session that you want to. You don't have to stick to the one that you registered for. I think there's 4. Anyone you want. I have on Moodle the schedule of all the demo times. So 2 of them will be led by me, 2 of them will be led by Dr. Casus. And essentially we'll be covering the same content. So you can sort of interchange them as you see fit. I would recommend that as much of your lab group goes to the live demos as possible. I will also post, my notes and a recording of the demo after the fact, with the intention that that should be kind of for like, oh, I forgot what she said about XYZ. I'm going to go back and review the footage, and let's see. So there will be 4 or 5 labs, probably 4. This is a little bit in flux at the moment because I'm planning a new lab this semester that I'm very excited about. And I'm not going to spoil it yet, but just, it's not just like exciting because I'm a professor and I like academic stuff. Like it's actually going to be cool, I think. Yes, that's all I'll say about that. I'll tell you more later. You're going to work in groups of 4. At last check, there's 35 people in this class, however, so we are going to have a group of not four, obviously. I have on Moodle a link to a Google spreadsheet. This is the spreadsheet that you're going to use to sign up to use the lab. And then there's another tab to sign up for a group. So if you have a group of 4 people you already want to work with, fantastic. Sign up for a team number. If you don't, no worries. I have a free agent list. So if you just put your name on the free agent list, I will put you on a team. All right. So this means if you have 2 or 3 people that you want to work together, but you don't have a fourth, that's okay. Just sign up the 2 or 3 and I will fill in additional members from the free agent list. Okay. So please do that by the end of this week. And I'll put a reminder on Moodle about that. Any questions on labs? No? Okay, cool. Last is there will be homework in this course. It is going to be on Moodle. And I have all of the homeworks set up as Moodle quizzes. So you put in the answers to the questions, though that gets graded for accuracy. And then there will be a last portion of the assignment that's worth the most points where you upload your handwritten work. All right, so homework, you will get some points for accuracy, but the most of your points will come from effort. All right, so I really care that you are putting in the time to work the problems and try it, more so than necessarily getting it 100% accurate straight away. So I hope that this is some incentive to not just, find a solutions manual, find the exact answer and type it into Moodle, because that's not valuable to you at all. Okay. All right. So kind of going into grades, the grade breakdown is in the syllabus as well, but just to show you the kind of percentages of stuff. So homework is 15% of your grade. All right. So that's a good chunk. So you should really put an effort into doing it. It will pay off on the exams, I promise. Each of the midterms are 20% each. Labs are 20% altogether. And then the final exam is 25%. All right, I try to structure my classes so that if you have a bad day on one of the exams, for example, it's not going to absolutely tank the entire grade, okay? That happens. I'm a person too. I get it. Okay. Last but not least, what do I do if I have problems or questions? Office hours is a great place to talk to me about really anything that you want. Homework questions, lab questions, preparing for the exam questions. Any of that good stuff is fine. Right now, I'm planning on Tuesdays. I think I said 1 to 2. Does that generally work for you guys, or do you all have classes at that time? It's okay-ish? Okay, I don't want to pick a time where literally no one's available. That's kind of defeats the purpose. I also can meet with you guys by appointment too. So just email me or email too. I'll answer questions by email. Sometimes if the question is in depth enough, I will ask you to just come by and talk because it's hard to, write math in an email sometimes. And then I mentioned you can ask me questions about lab and office hours. That's perfectly fine. You can also email me about the lab. The TA really should be the point person for especially lab equipment problems. In a pinch, I can help too, but she should be the main one. There's 2 TAs for this course. Our section TA is Ange, and I'll have her email on the syllabus, and I'll also put it on Moodle so you have easy access to it. And then Iju is the other section TA, but they both should be able to help you with lab stuff. So we kind of co-opt the lab with the other section. Okay. Oh, and I guess I should put my office is on the fourth floor of EC. And if my door's open, you're welcome to pop by too. Any questions on kind of how the class is going to run? Grades, anything? Okay. So we are going to start off this class with a little bit of review before we start introducing fluids. And that review is essentially some math recap. Okay, so fluid mechanics is quite a bit more math heavy, I guess I would say, than thermodynamics. But nothing we can't handle. That being said, if any of the stuff that I show you now feels really uncozy, let me know sooner than later. Okay? Okay. So first things first is derivatives. So we are going to have partial differential equations. We're not going to solve them as partial differential equations, but derivatives show up all over the place, right? And so I just wanted to remind you kind of what a derivative is. So if we have some function that depends on x, and it looks like this, and then we want to find the derivative of f with respect to x, we will define this in the following way. So essentially what we're doing is we can approximate actually, I don't want this arrow here. So we can approximate the slope of f at x and y as the following. And so I've put a partial derivative here. And this is a partial if f depends on more variables than just x. So x and y. So the derivative with respect to x will be a partial derivative. And so what we do is we say, okay, we can approximate our slope at x and y by making use of a point really close by, and we're going to call it x plus delta x and y. All right, so the distance between these 2 points relative to the x-axis is delta x. All right, and so we're just going to find the slope like how you would from very basic math, where we have rise over run. So we have our value of our function f at the location x plus delta x and y minus the value of our function f at x. And we're going to divide this by the distance delta x. All right, and so if we want to find our derivative, we're going to take this slope to the limit where delta x goes to 0. Okay? All right, and notation-wise, if we have a total derivative, I'm going to use just like Roman Ds for that. So this would be the case where f is only a function of x. HVAC's really loud, right? That's true. That's true. That's true. In this room?
It's just this room.
It's like the sound of a laptop that's gonna die. You know what I mean? Like when it.
Especially over the summer when we're in this classroom, okay, God, I'm just not stop.
Just like, yeah, it's really intense. Okay. Okay. So this is the definition of a derivative. Hopefully we feel pretty cozy with derivatives at this point. I'm not gonna be asking you to derive derivatives, but we'll make use of them, okay? The next thing that I want you to be aware of is quantities that are scalars. So scalars are quantities that are specified by a real number, but doesn't have direction. All right, so these are in fluid mechanics anyways. These are quantities like mass, temperature, uh, time, viscosity, etc. Okay. Now, if we have a quantity that also has a direction associated with it, that is what a vector is. So these are quantities specified by a real number which is a scalar. And in this case, it's called the magnitude. And also a direction. Okay, so examples of this are velocity, acceleration, and force. All right, quick note on notation. So this is the way that I will denote vectors. I will either use a arrow on the top of the letter. So this is what the velocity vector would look like. I could also use component notation. So the X direction component, the Y direction component, the Z direction component. Or you can write this out in the following way. So you have Vx I hat direction, Vy j hat direction, Vz k hat direction. All right, so I hat, j hat, and k hat are the unit normals in a Cartesian reference frame. Oh, that's ugly. Okay. Okay, so when we have vectors, there's a couple operations that we will want to be able to do with them in this class. The first one is the norm of a vector or the magnitude of the vector. So this is going to be denoted with double vertical lines. So this is for some general vector A. And it is just the square root of the sum of the squares of the components. All right, so we just have the square root of our X component squared added to our Y component squared added to the Z component squared. All right. Hopefully this is all fairly old hat so far. We will also be interested in adding two vectors. So if I have a vector A and B and I want to add them together, I'm just going to add together the scalar components in each direction. All right, so that looks like AX plus BX times I hat plus AY BY J hat plus AZ plus BZ K hat. Okay. We also might want to multiply a vector and a scalar. So if I have a scalar, lowercase a multiplied by my vector A, I'm just going to multiply each of the components by the scalar. Okay, so I have lowercase a times AX, I hat, plus lowercase a, AY, J hat, plus lowercase a, AZ, K hat. Okay. Oh, just like if I forget break, if I'm like writing at a ridiculous speed and you need me to like pause for a second, I'm not embarrassed if you tell me that too. So I'll try to look up and see if you're still writing and try to wait, but I'm excitable and I forget sometimes. Okay. Couple other operations that we need to have in our tool belt. And they involve essentially versions of how you would do multiplication if you have two vectors involved. All right. So if you multiply two vectors and you get a scalar in return, that is the dot product, or sometimes called the scalar product. And that looks like this. So if I have my same vectors A and B, the dot product just has a dot between them, as the name suggests. All right, and so this is going to give us a scalar back, right? So we need to essentially get the direction out of our two vectors, or get rid of it. And the way that we do that is we multiply the like direction components and then we sum them together. All right, so this looks like AX times BX plus AY times BY plus AZ times BZ. Okay. Also, a small note. The dot product is related to the angle between two vectors. Is related to the angle between two vectors. All right, and hopefully you remember this, even if it was a long time ago that you last saw it. But if I have my two vectors A and B, and they have an angle theta between them, it turns out that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of theta. All right. One other thing I wanted to mention is you might have noticed that if you do the dot product of A with itself, this is just equal to the square root of the magnitude of A. All right. Okay. The next sort of multiplication type operation that we can do between two vectors is a cross product or a vector product. So this is when we take our two vectors and we end up with a vector in return. And it looks like this. So if we have our A and B vectors and we do our cross product, I think most people do it this way. There's a few ways to actually work this out, but usually it's a determinant that you will do. So you'll have your unit norm vectors along the top row. And then you have the components of your first vector in the operation. So the leftmost one goes next, and then you have the right vector last. Is doing this determinant how everybody does cross products? Just want to make sure. Yes. Okay, great. All right, perfect. So to do this, what we do, and actually let me make a quick note. Order here is important. So you will get a different answer if you have B cross A versus A cross B. So just be mindful of that, okay? Okay, so when I work out this determinant, I'm going to start with this subdeterminant. So I have I hat times the quantity of AY BZ minus AZ BY. Okay. And then I have my next subdeterminant is the one in the J hat direction. So I have minus J hat times AXBZ minus AZBX. And then last but not least, we have our third subdeterminant. So we have plus k hat ax by minus ay bx. Everybody feels good about this? Okay, perfect. Okay. So this is pretty much all the operations that we need to have accessible to us for this class in terms of vectors. But we also are going to make use of, and this is actually very important, this next section, and we'll go over it a bunch of times until you guys are sick of me talking about it probably. So it's very important in this class that we can describe vectors with respect to a surface or a boundary, whether that surface is a physical, like hard material surface, or just a boundary through which fluid is passing, okay? And so essentially what we want to do is we want to be able to write any general vector in terms of a normal component and a tangential component relative to some position in space, whether that's a physical boundary or not, okay? And so how we're going to do that notation-wise is we are going to take any vector. Typically, it's the velocity vector, so I'm just going to use velocity in this case. And we're going to define it as a normal component, which is obviously in the normal direction, plus a tangential component in the tangential direction. All right, so if this is our vector v, and then this color. So this is my unit normal. All right, so this is a unit vector that is normal to the surface, just perpendicular. And then I also have a tangent normal. So this is just like our IJK, unit normal vectors that we have in a Cartesian sense. It's still Cartesian, but we're just basically aligning it with our surface, okay? And so what we have here then is our normal component of this vector v is going to be the part of the vector that's projected onto the normal direction. So if we just make a right triangle with that n hat and our vector, this side of our triangle is Vn. And then if we do that same thing in the tangential direction, so I'm going to make another right triangle. And this is our Vt. All right, so keep in mind, this is a right angle. This is a right angle. All right, so we're projecting our vector into those two different directions. All right, and so this is our normal component. And we can define our normal component as the following. So Vn is just our total velocity vector dotted with our unit normal n hat. Okay. One convention that we are going to be using all the time in this class is the following. So this dot product will be positive if the velocity is leaving our surface. And it's going to be negative when it's coming in. Or when it enters. All right, the reason for this is because we are using a convention where we're going to set up our unit normal always facing outward from our body, okay? So n hat is always going to point out from the surface. Okay. For our tangential component, so that is this guy. Is defined in the exact same way as what we did for Vn. So we just have our velocity vector dotted with our unit normal in the tangent direction, t hat. Oh, I forgot to say this. So as you're still writing, if you're still writing, when I was talking about projections of vectors onto the unit normals, the way I like to think about this, if that language isn't sitting super well with you, is the following. So if you shine a flashlight on your vector in this direction, the shadow that it casts is VT. And then if you shine it from a perpendicular direction, the shadow that it casts would be VN. Just another way to think about it. Okay. Any questions on decomposing into normal and tangential components at all? Okay. The next sort of type of quantity that we're going to deal with in this class is fields. So any quantity, this can be a scalar or a vector, defined over space is a field. All right, so for example, if we wanted to consider the temperature or the velocity of the air in this room that we're in right now, the air in here has a temperature and a velocity at every single physical location in space. And so we can define both those things relative to all of the spatial coordinates that we're used to working with, so X, Y, Z, and then also time. So for example, so if we wanted to write those quantities as a field, we would write the following. So we'd say that our temperature depends on X, Y, Z, and T. And all I mean by this is that any unique physical coordinate in space at any X, Y, Z location and at any given time, we have a specified temperature. And as we move around, that might change, it might not, but it has its own unique value. Okay. And then same thing for our velocity. Where it's important to note that when I say this, that also means that each of the scalar components of my velocity also depend on X, Y, Z, and T. So I have my X component depends on X, Y, Z, and T. My Y component depends on X, Y, Z, and T. And my Z component depends on X, Y, Z, and T. I realized that I forgot to mention something that is syllabus related, so I will do that now. I am going to reference kind of like where material is coming from the Fox and McDonald textbook. It should be on hold at the library if you don't have it and you want to reference it. I don't strictly require the textbook in this class, so after several semesters, I've talked to students and most of them said, we do just fine with the notes. And then others were like, well, it's a nice reference to have. So I reference it. If you want to look at it or check it out, that's great, but not strictly required. And then there was something else. Oh, the other thing I forgot to mention, this is just logistics. I teach a class right after this one in South Foundation Hall. So I have to like literally sprint from this building to that one right after this. Normally, I'm more than happy to like take questions and things like that after class, but with this like semester, I just can't. So I'm not being rude if I like run away after class, but just wanted to let you know. So yeah, I'll try to get here a little early instead. So if you have homework questions or lab questions that you want to ask before class, that's completely fine. Okay. All right, so let's now talk about fluids. All right, so we have kind of our background math stuff out of the way. And so next we want to define essentially what a fluid is. Does anybody want to take a stab? So this seems like a very easy question, but it quickly becomes kind of meta. All right. Any no wrong answers. What's a fluid? Yeah.
Is it like a substance where like the particles in it are free to move?
Yes, so technical. I love that. What's your name again? James. James, right? Okay, great. Thank you, James. That's fantastic. So a substance where particles are free to move. That's fantastic. Does anybody have any other definitions? So there's a couple that are probably from like elementary or middle school level that we usually discuss. Anything relating to states of matter, for example. James.
Can it like fill the container or something?
Yes, it takes the shape of its container, which I guess would also include cats. There was at least one cat person. Was it you, Sophia? Do you have a cat? Who mentioned having a cat? Oh, you did. Okay. Yeah. I am a dog person, but I've seen many cats taking the shapes of their containers. So, fantastic. A lot of times we'll also say a fluid is a liquid or a gas. And we should also include plasma. We won't be talking about plasmas in this class, but high energy density fluids are cool too. All right. So I am going to kind of restate the first definition that James gave us, which is the following. So fluids flow, whereas solids deform or bend. Okay, and if you start to think about that, like really sit with that idea, you can kind of start to see where the line between fluids and solids can get a little bit blurry. Right? Like if you look at a beam bending at a certain time scale, it probably looks like it flows, right? But with this statement, we need to say, well, what do you mean by flow, right? So I am going to expand on this by saying flow means to deform continuously under the application of a shear stress. And it does not matter how small that shear stress is. All right, another way to say this is that a fluid cannot sustain a shear at rest. Okay, so let's kind of think about what happens to fluids under a shear stress. So if we have a little block of fluid, all right, this is not in a box, it's just a chunk of fluid if you imagine it floating in zero gravity or something like that. And if we apply a shear stress to this thing, all right, so we're just gonna shear it, it will start to deform immediately. Not good. It's not good either. like so. Okay. I'd like to make an analogy with solid mechanics. This will probably be the only time that I do it because I'm not a solid mechanics person. So we'll talk about solid mechanics for like 30 seconds right now and then be done with that. All right. So you might remember, hopefully, looking at stress strain curves, right? Hooray. Can anybody tell me what generally this looks like for a solid? You can draw with your hands.
Linear line,
Yeah.
and then it goes a little curve.
Perfect. Okay, who can tell me about the slope of this line? Anybody remember? Yeah. It's the modulus of elasticity. Remind me your name again. Sorry? Daniela. Okay, thank you, Daniela. This is the modulus of elasticity. And this spot where it changes from being a linear curve, and remind me your name. I'm sorry, Preston. Okay. Does anybody remember what this is called? Yes. So this is the yield stress, and it happens at the point of yield. Okay. And so it turns out that fluids have an analogous property to the modulus of elasticity. So does anybody have a guess about what it might be? Oh, that would be a very, you know what, I would love that to be its name because it would be so like symmetric and make a lot of sense. But it is actually called viscosity. All right, so if you think about solid mechanics under this on this stress strain curve, our modulus of elasticity is going to give us some kind of indication of how easily that material is going to deform and then yield. And so viscosity is also going to give us our tendency of our fluid to flow. Okay, so you can kind of, we'll talk about it more in just a bit. And we're going to do our first lab on viscosity. But I like making this analogy because I think it's cool. Okay. All right. So now that we know what a fluid is in an academic sense, it's also important to mention that all fluids are governed by conservation laws. And, you know, all of nature is governed by conservation laws, of course. In 2500, we talked a lot about conservation of energy, right? In this class, we are going to be talking about conservation of mass, conservation of momentum, both linear momentum and angular momentum. However, in this class, we're going to talk about linear momentum. And when you finish this class and you realize I love fluids oh so much and you want to learn more, if you take intermediate fluid mechanics, we talk about conservation of angular momentum. Okay. We're also going to consider conservation of energy. But conservation of energy in this class will primarily be reserved for the unit that we, or the sections that we do on heat transfer. All right, so this is the first law of thermo that you know and love at this point. And then fluids are also governed by the second law of thermodynamics. which just says that heat never spontaneously flows from cold to hot. Or we would say that the change in entropy is always greater than or equal to 0. Delta S is greater than or equal to 0. Okay, so all of our discussion about fluids and heat transfer are going to be structured around one or more of these conservation laws, not necessarily all of them at once, but we will use this as the building blocks for everything that we do. And really all of engineering does this. So hopefully it feels comfy, cozy, and fantastic. Okay. Okay. When we're talking about fluids, we have two different methods of kind of analyzing them. And this is a very unique thing for fluids. So when we're talking about solid mechanics, these two choices don't really come up very much just because it doesn't make as much sense and it's not necessary. So fluids can be analyzed using either a control volume or a system. All right, we talked about this in 2500, right? So whether we're talking about an open system or a closed system, open systems use control volumes, systems use control masses. All right, so for example, if we have, I don't want to do this one anymore, but if we want to do flow through a nozzle, all right, so you can think of like a garden hose, for example, and we have an inlet and an outlet. So if this is our system, is it an open or a closed system? It's open, right? So we have mass coming in and out of it, so it has to be an open system. So we use a control volume. For all of you who thought you could just finish 2500 and forget it forever, I'm afraid that that's not the case. All right. All right. If we want to look at another system like a piston cylinder, so we have our cylinder, we have our piston, and then I don't like that either. And we have this cylinder filled with a gas. So if our system is the gas inside of this piston cylinder apparatus, is this an open or a closed system? It's closed, right? So we have no mass leaving or coming in. All right, so that's when we would use a system approach. Okay. Okay. Kind of analogous to this, we also have different ways to describe fluid flows. And they are a Lagrangian approach. and an Eulerian approach. Both of these are named after mathematicians, Lagrange and Euler. Fun fact, this is a really cringy joke, but I'll tell you anyways. Especially for, wait, you like to do math all the time, right? Okay, so if anybody asks you to quickly name 6 mathematicians as fast as you can just say Euler because there's 6 of them. There's like a family of geniuses. It's a fun little trivia fact. Okay, so the Lagrangian approach is the following. So we are going to follow individual particles as if they're little solid bodies, kind of. And when we do that, that means that we're going to track all of the information that we have about that little fluid particle, like position, velocity, acceleration, forces on it, all of that good stuff. Okay. In an Eulerian approach, we are going to, instead of kind of gluing ourselves to a little body and going wherever it goes and monitoring what happens, we're going to stick ourselves in one specific place and time and watch what happens and moves past us. Okay. So we will watch things flow past. And our view is fixed in space. The way I like to remember the distinction between these two different approaches is essentially with a traffic analogy. All right, so this picture on the bottom left is kind of, I should probably update this to make it more of, if you have a car that has any sort of semi-autonomous driving features, there's a camera on your vehicle that's tracking objects around you, right? So each of those objects have been detected and we're tracking its position, its velocity, all that good stuff. That is a Lagrangian approach, all right? We're looking at individual bodies and monitoring what each of them are doing individually, okay? Opposite, well, not opposites, differently from that, we could take an Eulerian approach, which would be more like a traffic camera on a telephone pole or something, or an overpass, where the camera is stationed in space and we're monitoring the flow of traffic going past that camera, where we're just kind of looking at what things are happening in aggregate rather than tracking individual cars. Okay, does that make sense? Okay, so for a fluid, does anybody have any thoughts on which of these approaches might be more convenient or better? The Eulerian one? Yeah. So Leo says Eulerian, and I agree. So tracking individual fluid particles, like in the Lagrangian approach, technically can be possible, but for very, very, very simple organized flows. So like if we're talking a laminar flow, like a sheet of laminar flow, that's maybe doable. But as soon as we start to look at something even slightly more chaotic, that becomes crazy unmanageable. All right. And so the Eulerian approach is essentially where we'll live pretty much all the time. Are you formulating a question? Oh, okay. You had the look of like a question. Oh, okay. There's so many parallels and everything. Okay, so for fluids, keeping track of individual fluid particles is usually unmanageable. So using an Eulerian frame is most common? Any questions on this so far? Yes.
So like, kind of like water, like through the nozzle, you wouldn't want to do the first one.
Oh, Lagrangian?
Yeah. wouldn't-
Yep. Mm-hmm.
And then is that for like water, gases, like all of that? You just kind of
Yep, pretty much everything. So just to kind of hopefully, I don't know if this will clear it up or make it more confusing, but in my research, I do a lot of research that involves solids and fluids. And I usually will do an approach that's called Euler-Lagrange. All right, so I do a blending of these two things. So for my fluids, I treat them as an oil, like in the Eulerian approach. So I just consider like I'm in this space and I'm watching things flow past me and I measure the velocity. But for all of the particles that are in the fluid, I track those ones individually. So I'll use a Lagrangian approach for that. So if you were thinking of like a river, and you're like dropping a stick over a bridge and watching where it goes, the stick you would track in a Lagrangian sense, but the river itself you would use Eulerian because you'd watch like the velocity as it flows past you.
Yeah.
Does that make sense? Yeah. Cool. Yeah. Great question. Oh, remind me your name. Luke. Okay. Thank you, Luke. Good question. Okay. Another thing, this is going to kind of seem like fluid mechanics potpourri. There's a few kind of topics that I'm just going to mash together in this unit, and so it doesn't flow real great. Pun intended. I'm sorry about that. Okay. So let's talk for a second about dimensions. And we did this in 2500 too, right? Yeah. So all the quantities that we care about are going to be defined in terms of primary dimensions. And we're going to stick with this in this class as well. It's extremely useful in fluid mechanics, although I'd argue it's extremely useful pretty much everywhere. But fluid mechanics champion this idea, I think. And our primary dimensions, just like how we had in 2500, are length, temperature, time, and mass. I will denote length as a bracketed capital L. Temperature is going to be a bracketed capital T. Time is a bracketed lowercase t. And then mass is a bracketed m. So each of these are not actually units. They just represent a dimension. Okay, so if I show you a bracket L, I just mean that's a length. You can use inches, meters, hectares, or whatever you want. It doesn't matter. But the SI units for each of these are the following. So the SI units, the SI units for length is meters. The SI unit for temperature is Kelvin. The SI unit for time is seconds. And then the SI unit for mass is kilograms. Okay. Just a quick note on units. So units are obviously extremely important as engineers. Bad things happen when your units get confused. On exams and in general, I will tend to use SI units because I prefer them, but there will be homework here and there that will use English units just because you should be comfortable with them. I'm sorry.
It's just that one problem at the end that's always so hard.
Because you need to do a weird conversion and it involves slugs. I know, I'm sorry. So that's my disclaimer. Okay, so an important thing that we need to realize is that all equations have to have dimensional consistency. This is a extremely useful tool if you are working out a problem, either in homework, on an exam, in the lab, what have you. If you're getting answers that seem not correct, checking the units is like a first line of defense to figure out what has gone wrong. So what I mean by dimensional consistency is that every term has the same units. All right, so if we have some expression that is A equals B plus C, it would be physically meaningless if A has units of meters, B has units of meters, and C has units of meters per second squared, right? What does that even mean? So we need to make sure that each of these terms, A, B, and C, all have the same units, okay? So that's what I mean by this. And then in terms of checking your work, if you feel like something wonky is going on, your results aren't passing the sanity check, it is always good practice to follow your units for the math that you've done for A, B, and C, and chances are you'll find out that one of them has the wrong units, and then you can kind of chase down where the error is from there. Okay, so let's do a quick example. And I'm going to use the Bernoulli equation. Okay, so our Bernoulli equation is that a pressure divided by density plus velocity squared over 2 plus g times z is equal to a constant. Okay, and I want to show that the left-hand side of this equation all have the same units. Okay. All right, so let's start with our first term. The pressure over density one. Okay, so I have pressure over density. How I like to do this is the following. So I like to break down my units into something that's a little more manageable, and I do it in a few steps usually. So I know pressure is a force per area, right? So I have a force divided by area. Those are not primary units yet, however, so we still need to do a little work on them. And then in the denominator, I have density. I know that that is a mass over volume, right? So mass is a primary unit, so, or primary dimension, so I can keep that in there. And then I'm going to say volume down here. Okay. All right. So first things first, let's talk about force. Force is mass times acceleration. All right, so I have mass. Now I have a primary dimension. And then I have times acceleration, which I'll leave for now. And then divided by area. Area is just a length squared. So I can put this into primary dimensions without too much trouble. And I'm going to do the same thing in the denominator with my volume. That is just a length cubed, right? So I will write it this way. So far, so good? Okay. So the last thing that we need to do is sort out acceleration. For acceleration, I just like to remember the unit for acceleration is meters per second squared. So that's a length divided by time squared, right? So this is a length divided by time squared. So just be careful with the t's. Lowercase is for time, uppercase is for temperature. All right, and now I have everything in terms of our primary dimensions. So I'm going to rewrite this out. So I have m times L divided by t squared. Oops. T squared. And then this whole thing is divided by L squared. All right. And then in my denominator, I have m over L cubed. Okay. Okay, so now that we have it in this form, we're just going to essentially simplify our fraction, and we're going to treat the m's and the l's and the t's essentially like variables, right? So if I have an m divided by m, that's just 1. And we'll reduce this. Okay, so my masses cancel. I have 1 in the numerator, 1 in the denominator. I have 1 length divided by L squared. So I just have 1 over L is how that works out. And then I'm going to, at this stage, I'm going to rewrite this again. Okay, so I have in the numerator 1 over t squared divided by L divided by 1 over L cubed. Okay, so this is a little bit of a mess, right? And so what we have here is I am going to take my 1 over L cubed in the denominator, and that flips into the numerator, right? So I have L cubed, and then I have 1 over L t squared, right? Okay, so this means that I can get rid of this L, and then this becomes a square. And so in the end, this one is L squared divided by t squared. I did the most painful one first. Okay, so this is how I approach dimensional analysis. So if you have a little bit of a hairy dimensional situation, this is how you would tackle it step by step. And then the other two are quite a bit simpler, so we can just check pretty easily the dimensions of these last two. So for velocity squared over 2, our units are velocity. So we have our dimensions of velocity quantity squared. So velocity is just meters per second. Typically, that's a length per time. So we have length per time, and that is squared, right? So we have a length squared over a time squared, which is awfully convenient because that's what pressure over density gave us, right? Okay. And we can also take a quick look at G times Z. So G is just gravity. And Z is a position, all right? So that's a length. So gravity is an acceleration. We already said that acceleration is length per time squared. And then Z is another length. So we, again, get length squared over time squared. Okay? If you ever forget the dimensions of something in a high stakes environment like an exam, like for example, you don't remember what the units of pressure are. You can take an equation that you know is true, right? We know Bernoulli is dimensionally consistent, and you can say, well, GZ, I know what the units of G times Z are, and I can just back out what the units of pressure must be because I know they have to be the same. Okay, I've done this before. Okay, so yeah, don't panic. There's dimensional analysis. Okay. I don't know. Well, we'll see. I'm going to try and get through experimental uncertainty. Actually, let me ask you guys, how do we feel about calculating experimental uncertainty with like the equations? Don't be shy. Do we want to see it again? Because I don't mind doing it again if you want to see it again. Yeah? Okay. Okay. I don't know if we'll get all the way through it, but we'll try. Okay. So experimental uncertainty, I am showing it to you in lecture right now. I'm not going to test you on it in exams, but you're going to use it in lab. Okay. So, we're going to do it now, but just keep in mind, except for I think I might have one homework question about it, but mostly it'll be a lab exercise, okay? Okay, so when we're talking about error, errors are always present anytime we make a measurement. All right, and so these errors are going to fall into two categories. There's fixed error and there's also random error. Okay, the difference between these two is the following. So for fixed errors, we are talking about an error that's the same for every single measurement. And these types of errors typically can be reduced with calibration, for example. Okay, so if you were doing an experiment where you needed to measure the mass of something, for example, and your scale was not calibrated correctly, you would have a fixed error for every single measurement. That is a direct result of kind of the uncertainty of that equipment itself. And if you recalibrated it, you could not eliminate, but reduce that error, okay? On the other hand, random errors are errors that are non-repeatable. You cannot remove them, and they're different for every single reading, okay? So random errors, sometimes called non-repeatability. They can't be removed. And they're different for every reading. Okay, so if we want to estimate error, which we do, oh, sorry, yes, go ahead. Jaden, right?
Yes.
Okay.
So for like random error here, you have a resistor that has a plus or minus 2%. That would be random or fixed?
So that would be fixed. That should be more fixed. So you would expect that same plus or minus 2% every single.
So even if it's less or even if it's greater, it's still considered fixed, like a fixed error.
So this one is a little bit nuanced. So typically for that resistor or for equipment in the lab, a lot of things will say, assume the error is plus or minus whatever percent, right? So that is actually truly a random error that they've measured a bunch of times and told you what the plus or minus 95% of. Right. So it's a truly a random thing, but we're treating it as fixed because someone's already aggregated the randomness into a value that we can just use. Does that make sense? Okay. So when we're in the lab, anytime we take a measurement, do calculations with those measurements, those values are essentially meaningless without saying something about the error. Okay. So you can calculate the velocity. So if you were, caught speeding and the person told you you're going 100 miles an hour, that means something entirely differently if the radar gun has an accuracy of plus or minus 20 miles an hour or plus or minus 2, right? We're talking about different things. So the error is really important to note when we're talking about things in the lab and as engineers. Okay, so in order to do this, we are going to follow 3 steps. The first thing that we're going to do is we're going to estimate the uncertainty level for every single measurement. All right, so everything that you are measuring in the lab should have an uncertainty level associated with it. And then we are also going to state the confidence level on each measurement. So for example, this would be the height of something is 2 plus or minus 1/64 of an inch. Okay, and then the last thing that we're going to do is we are going to analyze the propagation of error through any calculations that we might have to do. Okay. Okay, so when we're talking about uncertainty level, I want to give you a little bit more of a statistical nuance of what we're talking about that. So when we are talking about uncertainty levels, there we go, I want that color. If you imagine that you are, say, measuring the length of something, right? So you have your ruler or whatever you're using to measure, and you're going to repeat the same measurement for a single object multiple times, like tons and tons of times. Obviously, we're not going to do this in the lab in practice, but if you were to do this, you would end up getting measurements that look Gaussian. All right. So this would be the number of occurrences or measurements or readings. All right. And this would be, for example, the value measured. Okay. So this is a Gaussian distribution. All right, and you'll notice that we have a peak number of occurrences that happens in the middle, of course. So this is your mean measured value, or the nominal measured value is sometimes called. And then if you were to have repeated this measurement exercise enough times that you get a nice distribution that looks like this, you could calculate your uncertainty using properties of this Gaussian distribution. So uncertainty is defined as plus or minus and sigma. So this is our standard deviation. So if you would have one standard deviation, this is 68% of the measurements would fall within that band. If you have two, that would give you 95% of the measurements within that band. And then let me scooch this over a little bit more. And then if you do three, that is 99% of the measurements. Okay. This is not typically practical to do, right? So if every time you needed to measure something in the lab, typically we're taking measurements of lots of quantities. So if you imagine having to take that same measurement over the same conditions like 100 times, lab would take forever. And that's, largely impractical. So what we do instead we will use plus or minus half of the smallest scale division. All right. Or we will use whatever the manufacturer has given us. Okay. So if the equipment gives you the plus or minus whatever percent to use, you can assume that they have done that repetition of measurements, done their Gaussian curve, and they have calculated that for you. Okay. Does everybody feel okay with the half of the smallest scale thing? Okay. Perfect. Okay. I have some examples, but I'm going to save them for next time. So next time we will I'll just recap and then we'll dive into the example.